A Manhattan skyscraper can buy heat almost the same way it buys electricity. Beneath the street, a network of pipes carries steam into office towers, apartments, hospitals, and landmarks. Con Edison says that network includes about 105 miles of mains and service pipes. It began operating in 1882, and it still helps buildings make heat, hot water, cooling, and specialized services. So the real question is not why steam rises from a striped street stack. It is why modern Manhattan buildings still choose to buy energy from a system this old. Start with the basic transaction. A generating plant heats treated water and produces steam. Pressure moves that steam through large underground mains. Smaller service pipes branch from those mains and enter customer buildings. Inside, the steam reaches equipment that transfers its energy into the systems people actually use. The network is the delivery system. The building still controls what happens after the connection. That distinction matters. District steam does not mean that the same cloud drifting above the street is being pumped into every apartment radiator. A commercial building may use a heat exchanger to warm its own water loop. Another may use steam for domestic hot water. A hospital may need it for sterilization. A large building can even use steam to drive an absorption chiller, equipment that turns thermal energy into cooling without using a conventional electric compressor for the entire job. Think of it as a shared thermal utility. Instead of every connected building producing all of its own thermal energy in a basement boiler plant, part of that production happens elsewhere. The customer buys the delivered steam and uses it through building-side equipment. The exact arrangement differs from one address to another, but the organizing idea stays the same: centralized production, a distribution network, and many separate customers. Once steam becomes a utility, one old boiler is no longer the right mental picture. The useful unit is a network. And networks survive for different reasons than individual machines do. The scale changes the story. In its fiscal year 2025 filing, Con Edison described this as the largest steam distribution system in the United States. The company reports roughly 105 miles of mains and service pipes, supported by about 3,000 steam manholes. That is active utility infrastructure, not a preserved industrial exhibit. The same filing says the system delivered about 16,975 million pounds of steam in 2025. Put more naturally, that is nearly 17 billion pounds in 1 year. It went to approximately 1,490 customers in parts of Manhattan. Those customers are not equal dots on a map. A hospital, an office tower, an apartment complex, and a small commercial user can have very different demand. That is why dividing annual steam by the number of customers would create a neat number and a bad explanation. The important point is the relationship. A large network still serves a concentrated group of buildings at material scale. The customer number can also sound smaller than the system really is, because the filing counts utility customers, not the people, hotel rooms, offices, or hospital departments served behind each connection. One customer account may represent a large building with thousands of daily occupants. The network is wholesale in appearance and intensely local in effect. A pipe enters one property, then the building's own systems distribute the useful heat through many interior spaces. The system is also narrower than the phrase "Manhattan runs on steam" suggests. It serves a corridor in parts of the borough, not every block and not every building. The title captures the surprising utility. It should not be mistaken for a claim that the entire island shares one heating system. The first job is the obvious one. Steam carries thermal energy that a building can use for space heating. But the same incoming service can support more than warm rooms. It can help produce domestic hot water. It can support humidification, cleaning, or other building processes. In some hospitals, steam can serve sterilization equipment, where dependable high-temperature service matters directly to operations. In commercial buildings, it can also supply absorption chillers. Those machines use heat as an input to help produce chilled water for air conditioning. Not every customer uses every one of these functions. That would depend on the building and its equipment. But the range matters because it changes what replacement means. If a property uses the connection only for heating, the owner faces one kind of project. If the same steam service supports heating, hot water, cooling, and a specialized process, removing the connection can create several projects at once. Picture a hotel. Guests need hot water before sunrise. Public spaces need heat in winter. Cooling loads rise in summer. Kitchens and laundry add their own demand. A single steam connection can feed equipment that supports several of those needs. The network does not eliminate the mechanical room, controls, or maintenance. It changes which production equipment must live inside the building. That is the first real answer to why the system survives. Buildings do not keep the connection because steam looks historic. They keep it because the service can still do useful work. And the more jobs tied to that service, the less accurate it becomes to describe replacement as simply cutting out an old pipe. Now place that decision inside Manhattan. Mechanical equipment needs floor area, shafts, ventilation, electrical capacity, structural support, and access for installation. In a dense building, none of those are abstract. A basement room can compete with storage, retail, parking, back-of-house operations, or other equipment. A roof can already be crowded. A new riser can pass through occupied floors. District steam moves part of the production problem outside the customer building. The property still needs equipment to receive and use the steam, but it may not need the same on-site plant that would be required to produce equivalent thermal energy from scratch. Con Edison argues that this can preserve building space and avoid some of the disruption associated with a deep retrofit. That is the operator's case, not proof that steam is cheapest or best for every property. Different buildings can reach different answers, but the argument explains why an owner cannot evaluate the connection by looking only at the age of the network. Consider a simplified replacement. The owner may need new heating equipment, pumps, electrical work, controls, and a different path for hot water. Cooling equipment may need to change too. Heavy components must enter the building somehow. Existing tenants may need service interruptions. None of that makes replacement impossible. It makes it a building project rather than a utility cancellation. The order of work matters as much as the equipment list. New systems may have to be installed while the old steam connection remains available. Temporary service may be needed. Rooms built for one arrangement may not have the clearances, airflow, or access needed for another. A technically attractive end state can still require a difficult construction path. For a building owner, the transition happens in occupied space, on a schedule, with tenants expecting normal service. This is where density becomes part of the technology. A solution that looks inefficient on an empty site can make more sense when space is expensive and the building already has a working connection. The network's value is not stored only in the pipes. It is also stored in the way customer buildings were designed, renovated, and operated around those pipes. That installed relationship creates inertia, but inertia is not the entire explanation. A useless network can still be removed. A useful network connected to many constrained buildings is harder to replace because it continues to solve a real problem, while the alternatives create new work inside each property. The network's geography reinforces that point. Public planning documents describe a service corridor running from Lower Manhattan north into parts of the Upper East and Upper West sides. It follows the kind of dense commercial and residential territory where a shared thermal service can connect many large users within a relatively compact area. But connection is not automatic. A building must be within reach of the system and must have suitable customer equipment. Properties outside the service area solve the same heating and cooling needs in other ways. Even inside the corridor, not every building buys steam. That boundary is useful because it prevents the story from turning into a claim about some unique law of New York architecture. Manhattan does not require steam in order to function. It contains a long-established district system that remains practical for a specific group of customers. The system's concentration is part of its strength, and its limited footprint is part of the truth. The stripe stack is the network's most visible object, but it is easy to read it incorrectly. The stack's job is to redirect hot vapor above pedestrians and traffic. It creates separation between street level and whatever is producing the visible plume below. One possible source is a steam leak that the operator is managing. Another is ordinary water reaching very hot steam pipes or hot surfaces inside a manhole. Rainwater, a water main leak, or other street water can heat rapidly and become a large cloud of visible vapor. From a distance, both paths can produce the familiar New York image. That does not mean every plume is harmless, and it does not mean every plume marks a broken steam main. The stack tells you that hot vapor is being moved upward. It does not diagnose the cause by itself. Con Edison's safety guidance says people should stay away from steam escaping directly from a manhole or a crack in the pavement and report it. The useful lesson for this story is simpler. The street cloud is only the visible edge of a much larger operating system. Once you understand the stack, the image stops being a piece of New York atmosphere and becomes a clue. Something beneath the street is hot, active, and being managed. What you see above ground is not the network itself. It is one point where the network becomes visible. New York's steam service began in 1882. That date explains why the system feels like industrial archaeology. It does not mean the current network is a set of untouched Victorian pipes. An operating utility is maintained, repaired, and changed while the city around it changes too. History matters because it created the installed relationship. Mains reached dense blocks, buildings connected. Mechanical rooms were designed around delivered steam. Later renovations inherited those choices. Each working connection made the network relevant to another property, while the network made delivered steam available to the next customer. But age cannot carry the whole explanation. Many old urban technologies disappeared when they stopped providing enough value. This one still performs current building jobs. Its survival comes from both parts of the story: the cost and complexity of changing an installed system, and the continuing usefulness of the service that system provides. The past built the network. Present-day buildings keep making decisions about whether to use it. Centralized production can solve a building space problem. It does not automatically solve a carbon problem. Con Edison's current steam overview says more than 97% of its steam production comes from natural gas at 5 company plants. The system also receives contracted steam from the Brooklyn Navy Yard. That makes the present network a major gas-dependent utility, not a carbon-free source of heat. This creates an important separation. The pipes are one design choice. The fuel and equipment that produce the steam are another. A distribution network can remain useful even while its energy source becomes the central problem. That distinction opens 2 broad directions. One is to replace steam service building by building, moving more production equipment and energy demand inside each property. The other is to keep useful parts of the distribution system while changing how the steam is produced. Real planning can combine those directions, and the right answer can vary by customer. This episode cannot prove which path will win. What it can show is why the question is more difficult than old technology versus new technology. Electrifying a building is not merely a fuel swap if the building also needs new equipment, electrical capacity, and distribution work. Decarbonizing central steam is not merely a pipe question if the production plants remain dependent on natural gas. The 2 approaches also distribute risk differently. A building-by-building transition creates many separate engineering projects, each shaped by one property's equipment and constraints. A production-side transition could affect many customers through shared infrastructure, which makes system performance and planning especially important. Neither description proves a preferred solution. It shows why decisions about the future of the network involve utilities, buildings, and public policy at the same time. The network's centralization may offer a different transition path from replacing every connection. That is a possibility, not a completed result. Con Edison has discussed lower carbon pathways, but current fuel data still defines the present system. So the quality that helped steam survive now creates a larger responsibility. A utility shared across many buildings can concentrate equipment outside those buildings. It can also concentrate the challenge of changing the energy source that feeds them. So why does Manhattan still run on steam? First, the phrase describes an active utility in parts of the borough, not a museum piece, and not every building. Second, one connection can support several jobs, including heating, hot water, cooling, and specialized processes. Third, dense buildings may avoid some on-site production equipment, while replacement can require space, electrical work, and disruptive changes inside occupied properties. Those benefits will not be equal for every customer, but they explain why removing the network is not a simple modernization switch. The system's age made it familiar, its continuing usefulness kept it relevant, and its dependence on natural gas now prevents an easy environmental victory lap. The strange thing is not that a technology introduced in 1882 survived. The strange thing is that it kept solving a modern building problem long enough to inherit a modern energy problem. The next time a white plume rises above a Manhattan street, the stack will still be the first thing you notice, but now you can picture the rest. A plant, a main, a service line, a building connection, and several systems depending on the heat delivered through it. The visible cloud lasts a few minutes. The utility beneath it has been shaping building decisions for well over a century.